This is a video on assorted calculus problems focusing on finding extrema. And so we start with number 1, which simply says find the absolute extrema of f of x equals 1 over 1 plus x squared for the interval 1 comma 2. We'll do this in two ways, one super simple way and then one way using calculus. The first way, if I'm looking at this function, it's not undefined anywhere because I can't get that denominator to equal 0 for any real numbers. And what happens, where's the maximum of that function? Well, 1 plus x squared has a minimum, which would be the maximum of this function, at x equals 0. Because for any other value, x makes the denominator bigger, which makes the whole fraction smaller. So what is the function when x equals 0? It's simply at 1. Any positive values are going to give me the same thing as negative values because that square is going to cancel them out, and it's going to make the function smaller, and it's going to approach 0. So we have a function that looks like this. So I already cheated a little bit because just from my graph, I know that the absolute maximum here, the absolute maximum for number 1 is going to be 1, and the absolute minimum is going to be 2, because it is a function that on that interval, say, I don't know, this is 1, this is 2, on that interval, we are strictly decreasing. So we know that the endpoints represent our maximum and minimum. But how do we get that using calculus? We just take the derivative of the function, 1 over 1 plus x squared. I can use the quotient rule, or I can just say this is equal to 1 plus x squared to the negative 1. And I can take the derivative of it, which gives me negative 1 times the derivative of the inside. So the derivative of the outside is negative 1 times 1 plus x squared to the negative 2. The derivative of the inside is 2x. And that's my product rule, or that's my chain rule. So I end up with negative 2x over 1 plus x squared squared. And so we have a bunch of things we need to check. We can check our endpoints by plugging them in. And we can check to see if we have any derivative equals 0 points, which would be other possible extrema. So we set our derivative equal to 0. On that interval, our denominator is never going to equal 0, so we just multiply the denominator across, and we get negative 2x equals 0. Divide by negative 2, and x equals 0 is our only other point of interest here on this graph. It's the only other point where our derivative might be 0, where we might have a local max or a local min. And you can see from my graph why that is, because right at 0, that's where we have a maximum going on. But that doesn't matter to us, because we have this function. So since we just proved that in the interval the function is either strictly increasing or decreasing, all we have to do is plug our endpoints into here and say which point is bigger than the other one. So if I plug in 1, f of 1, I get 1 over 1 plus 1, which is a half. So at f of 1, y equals a half. And at f of 2, if I plug in 2, I get 1 over 1 plus 4, which is 1 over 5. Clearly 1/5 is smaller than 1/2, so our extrema are, let's say in our range, our global minimum is x equals 1, and our global max is at x equals 2. Or y equals 1/2, y equals 1/5. And that's that problem. Number 2 says, given this ugly function, x squared plus y squared equals 2x plus y to the 4th, or plus 4y, dx dt is equal to negative 5. We're assuming this function is differentiable in terms of t, because we're asked to find dy dt at a given point. And we just remember implicit differentiation. If I'm taking d dt of this whole function of x squared plus y squared and setting it equal to d dt of 2x plus 4y, I simply take the derivatives, so I get 2x dx dt plus 2y dy dt equals d. So on the other side we have just a 2. The derivative of 2x is just 2. dx dt plus the derivative of 4y is 4. dy dt. And now we have a bunch of variables. We have 1, 2, 3, 4 variables, but luckily for us, we have 1, 2, 3 plug-in values. 4 variables, 3 plug-in values means we can solve for the last piece. So dx dt is equal to negative 5. So anywhere I see a dx dt, I'll plug in negative 5. Anywhere I see an x, I'll plug in a 3. Anywhere I see a y, I'll plug in a 1. 2 times x is 3 times dx dt is negative 5 plus 2 times y is equal to 1 times dy dt, I just keep it, equals 2 times dx dt, which is negative 5, plus 4 times dy dt. And now when we simplify a little bit here, it becomes a very easy problem. I'll do this piece first and get 2 dy dt. 2 times 3 times negative 5 is going to be negative. 3 times 5 is 15, times 2 is 30. And then we have 4 dy dt minus 10. Skipping ahead a little bit, we add 30 to the other side and we get 20. We subtract 4 to the other side and we get negative 2 dy dt. So dy dt is equal to negative 10. So if I were to plug in negative 10 to that derivative function, I should get the same thing on both sides. And that is all we do if we're differentiating in terms of a different variable, a variable that we aren't using in our equation. We differentiate implicitly, and we end up with these things. Our derivatives in terms of that other variable, and then we just solve it out. Number 3 asks that we find the local minima of the function f of x equals x minus 2 cubed x plus 3 squared. I think this one is simply the easiest way to do it would probably be just to take the derivative, so we'll go through that now. F prime of x is equal to, we will do the product rule, so I'll take the derivative of this piece first. The derivative of the inside here using the chain rule is just going to be 1, so taking the derivative of the outside is easy. 3 inside to the power of 2 times the other function, x plus 3 squared. And then with the product rule, we put a plus sign, and then we take the derivative of the other piece, the derivative of this piece, which is 2 x plus 3, nothing to pull out, and we multiply it by the other piece, which was x minus 2 cubed. And that's our derivative. And now notice with my derivative here, I have a piece that has a lot in common with another piece. And usually in math, if I have something like x cubed y squared plus x squared y to the 5th, something like this, the natural idea is, well, let's factor it. Let's pull out what they have in common. And if I pull out what they have in common in my little example here, I would have an x squared on the outside times a y squared on the outside. And on the inside, I would have x times 1 plus, I pulled out an x squared, so it's 1 times, and I pulled out 2 y's, so y cubed. And so I apply that same rule to my problem up here. I say, what can I factor out of both of those terms? Well, they both have at least 2 x minus 2's. They both have x minus 2 squared. They both also have at least one x plus 3. They both have an x plus 3. And that is going to be being multiplied by whatever's left on the inside, whatever's left here. So what's left here when I take away 2x minus 2 squareds and 1x plus 3? Well, I had 2x plus 3s, take 1 away, and I'm left with 1x plus 3. And I didn't do anything with this 3. I didn't take it out, so I'll leave the 3 up front, and I'll continue. I'll put my little plus sign, and I'll go to this side. What's left here when I take out 2x plus 2s, or 2x minus 2s? I took 2 of them away from 3. I get 1x minus 2. I took away this whole x plus 3 and put it right here, and I didn't touch the 2, so I'll put the 2 up front as well. And this is still f prime of x. All I did was factor a little bit, and that factoring gets a lot prettier once I multiply this out. So I get f prime of x is equal to x minus 2 squared, x plus 3, and 3x plus 2x is going to be 5x, and 3 times 3 is 9. 2 times negative 2 is minus 4. 9 minus 4 is positive 5. And so we got to the point that we were looking for. We now know that our f prime of x is equal to 0. If we set it equal to 0, our f prime of x is equal to 0 when x equals positive 2, when x equals negative 3, and this last tricky one, we could factor out of 5, so it's when x equals a negative 1. And that's half the battle. That's a big portion of what we wanted. So now we know where we have local extrema. The problem being, those extrema could be, if I have my little graph, they could be maximums, they could be minimums, or they could even be saddle points. They could be points that look like they're about to change and then switch back at the last minute. So let's talk about how to find a minimum or a maximum, how to find out whether your critical point is a minimum or a maximum. The first thing you learn in calculus is the first derivative tells you, for example, the first derivative of this function would tell you that the slope is always increasing. The first derivative of x squared is 2x, and 2x is always increasing as x increases. So the slope tells you that your slope is going from negative, it's going from very negative to it's approaching 0, 0, 0, it gets to 0, and then it gets really, really positive. Your slope is increasing. Now, let's say we have the graph of the slope. What the second derivative tells you, f double prime of x, will tell you whether the slope is increasing or decreasing. So now let's look back at the graph I have here. Is my slope increasing or decreasing right here? Well, my slope is going from a positive slope, it's equaling out at 0, and then it's going to negative. Now we have negative slope right now. And so, as we go from as our slope is going down, 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 you see that we have a local maximum. So we have a local maximum when the slope of the slope, or the second derivative, is a negative value. I shouldn't put an x there too. Is some negative value. And if we look at a local minimum, we know that if the second derivative is, as we go down, the slope is actually increasing here. It's going from really negative to a little more positive, then 0. Now the slope's officially positive, getting more and more positive. So we know here that if the second derivative, if f double prime of x is equal to a positive y, to some positive value, then we have a local minimum because the slope is working its way up. It's working its way to being increasing. Well, the slope is increasing. The function's working its way up. So all we have to do now is take our second derivative, plug in our critical points, and if we get a negative value, we know that we have a local max. If we get a positive value, we know we have a local minimum. So this is a maximum, this is a minimum. So the hard part, finding the second derivative. Give myself some more room. And let's find the second derivative. So to do that, I'm going to use the product rule, but I have 3 pieces, which is a little scary. So I'm just going to multiply the right 2 pieces together. So I'm going to get that f prime of x is also equal to x minus 2 squared. And I'm just going to multiply the right side out a little bit. It's going to give me 5x squared plus 5x plus 15x plus 20x plus 15. So all I did was multiply those right 2 pieces out. And now taking the second derivative is very easy. F double prime of x is just equal to the derivative of the first piece, 2 times x minus 2, times the second piece, 5x squared plus 20x plus 15, plus the derivative of the second piece, which is 10x plus 20, times the first piece, x minus 2 squared. And now we just have to plug in our points. And to remind you, our points were x equals 2, x equals negative 3, and x equals negative 1. And if we plug in these 3 points, if we get a negative value, we know we have a local max. If we get a positive value, we know we have a local min. So we'll start with, we'll just do them in order. We'll start with x equals 2. Well, I see here, x equals 2 is going to cancel there, x equals 2 is going to cancel there. We're going to get zeros in both of those spots. And so we have f double prime of 2 is equal to 0. It's not positive or negative. So one might assume that we have a saddle point. We have one of these points where we think it's going to switch, but it doesn't really. But we don't have to worry about that. We just know it's not a max or min right now. And we push forward. We look at f double prime of negative 3. So let's just plug in negative 3 here. We get 2 times negative 3 minus 2. I'm right here. Negative 3 minus 2 is negative 5. Times, well, negative 3 times negative 3 here. Negative 3 times negative 3 is positive 9. Positive 9 times 5 is 45. Plus negative 3 times 20 is actually going to be a minus 60 plus 15. And we see 45 minus 60 plus 15, that term's just going to cancel. This whole term dies because we have a multiplying by 0, and we just have to plug in the negative 3 over here to see what happens. I plug in negative 3, I get 10 times negative 3 plus 20. And it's going to be times a positive value because it's something squared. It's something squared. So all we have to really care about is this piece. And 10 times negative 3 is more, so we get negative 30 plus 20 is negative 10. So our negative 3 is going to be a local maximum. Our negative 3 is a local maximum, so we don't care about it. We're looking for minimums. Or we can just say, if we're looking for all extrema, x equals negative 3 is a max. And our last step here is to plug in negative 1. So let's see if I can just delete this piece. You can always go back in the video to look at it if you need to. And let's plug in negative 1, f double prime of negative 1. This is equal to 2 times negative 1 minus 2 is negative 3 times 5 minus 20 plus 15. And we see once again, this whole piece is going to cancel because this piece right here equals 0. So we just need to look at the second term, which is negative 10 plus 20 times something positive because it's something squared. And negative 10 minus 20, or negative 10 plus 20 is a positive 10. So x equals negative 1 is a minimum. Because once again, f double prime of x equaling a positive number gives us a minimum. So there is the answer to our... Does f of x equal 10x plus 3 times the third root of x to the fourth have a vertical tangent line at x equals 0? Well, let's take the derivative of it and see. If I take the derivative of this, I get 10 plus. The derivative of this piece is a little tricky, so let's work through it. We have 3 times x to the 4/3. And the derivative of that is, well, the derivative of the x term is just 4/3. 4/3 times 3x to the, subtract 1, 1/3, which gives us 4 cube root of x. So we get 10 plus 4 cube root of x. And when x is 0, this solution is 10, which means it's defined. So f of 0 equals 10, which means the solution is defined, which means there's no vertical tangent line. Because when you're graphing something, if it's a function at that point, if it passes the, if it's pretty continuous at that point, it's never going to have a vertical tangent line. It will only have a vertical tangent line if we have something that goes off to infinity in either direction. So the answer is no, it does not have a vertical tangent line at x equals 0.